Good evening, everyone, and thank you for coming to my talk. So I'm going to talk about aircraft endurance. So the agenda today is I will do a quick introduction talking about cyclic loads on aircraft, the phenomena of metal fatigue, and also material property in terms of SN curves. Then I will move on to part 2, that is stress ratios, and mainly notches and cracks. Then finally, I will talk about advanced manufacturing technologies and new materials, how they can help to improve the durability and the damage tolerance. I will focus on metallic structures first, and I will finish with polymer composites and give a summary and outlook. I try to finish my talk in 40 minutes, and I will answer questions at the end. So firstly, I just want to show you a glider, and that has a graphic presentation of cyclic loads. So I can't show this on large aircraft because it wouldn't have this kind of cyclic loads graphically. So all I want to say is aircraft loads are cyclic, so fluctuating, and in the air we have atmospheric turbulence load, and that has the frequency about 0.5 Hertz to 1 Hertz, cyclic loading. On the ground, we have taxi load before the takeoff and after landing, and that is also quite severe on the wing. And in the fuselage, the cabin pressure load is 1 cycle per flight, but that is quite high because of the pressurization in the sky. So fatigue has been the most critical failure mode for airframe. So the lower picture you're seeing is a wing model we did in finite element, and showing the air loads and in the cyclic nature, and also the hot spots tend to be in the wing root. So the wing is like a cantilever beam. So why metal respond to cyclic loads? Because metals are crystalline in nature. So the atoms are arranged in an ordered manner. So most structured metal materials are polycrystalline and consisting of a large number of individual grain or crystals and in an ordered manner. So dislocation will happen even under the tension static load, and that will move along the crystallographic planes and causing the onset of sleep. So what my mouse shows is a sleep band within the grain. And that sliding will cause the grain moving relative to each other, to the neighboring grain. And this is true for both static load and the cyclic load. But under the cyclic load, the sleep band can progressively moving in the forward and the reverse manner because we're doing cyclic load. So eventually we have extrusion and intrusion pairs, and that is resulting in the formation of fatigue crack, and this is the famous Woods model. So we now got a cyclic loading, and we have a crack initiation in metals explained. So the definition of metal fatigue has an official one in the ASTM standard, but that is very long for professional fatigue research. I quite like this one I got from Open University lecture notes. And that says fatigue failure is the formation and the propagation of cracks due to the repetitive or cyclic load. The second line is quite important. That says most fatigue failure are caused by cyclic loads that are significantly below the loads, and that would result in yielding of the material. That says even your load are much lower than the yield strength, but is applied in the cyclic manner, fatigue will happen. So the first person studied fatigue is Mr. Wohler in 1850s. So that's 170 years ago. He studied progressive failure in German railway axis, the structures. And he actually invented the first fatigue test machine. Shows here is a rotating bending machine. We have one in the faculty, but much more modern now. So basically this axis bar was attached by two springs on the substrate base, applying bending moment. But this axis also rotates. So the bending moment introduced the tension and the compressive stress was actually applied cyclically as you rotate. And Wohler discovered the concept of fatigue strength for the first time in the world. And it really says even the stress is much, much lower than the yield strength, metal will fatigue and the cyclic load. So just want to show Wohler curve. And Wohler curve actually shows the applied stress versus number of cycles to failure. And these points were original Wohler's testing point. And you can see as the stress decreasing, the fatigue life will be longer. So that was his discovery, and was the first person to correlate this relationship. So we don't have a fatigue machine, but I hope you have a clip, a paper clip, and you can actually extend this metal wire like this. I hope you can see. And you can do the cyclic bending test in my class. And hopefully just before I finish the lecture, your metal wire will fail. If you only bend once, you would not fail statically because it's ductile material. But if you do it cyclically during my class, it will fail by fatigue. So the modern treatment of Wohler curve, we call it SN curve, where S stands for stress applied and N stands for number of cycles to failure. So we call it SN curve, but some people still call it a Wohler curve. And just want to say SN curve is a material property and the cyclic load. So it's nothing to do with the geometry. If you have a material, you do cyclic loading, it will produce a correlation between applied stress and the number of cycles to failure. There is a fatigue limit marked by the green point, and that is asymptote tendency. So the SN curve turns to an asymptote to the horizontal level. And that is true for steel alloys, for ferrous alloys. That really means if your applied stress is below the fatigue limit, there will be no fatigue. In theory, your structure will last forever. However, lowering applied stress in engineering design often means overly conservative design, and that will lead to increase in weight, increase in the fuel consumption, and the CO2 increase, and also the cost of the parts. Therefore, reducing stress is not always in the design envelope. The second thing I want to say is in service, we don't really have a fatigue limit stress because service loads are variable. You could have a bad weather, a big gas loading in the aircraft, or a heavy landing. So fatigue limit does not exist in real structures. The final thing I would like to mention is stress raises on component. And that is a large cutout, fastener holes, cracks, and joints with a geometry discontinuity. And that is the one I would like to talk today, the stress raises. So the first example I want to say is the de Havilland Comet aircraft in 1952. And that was the first jet passenger aircraft with pressurized fuselage for the first time. So it's very comfortable for people to travel with pressurized fuselage and large square windows. And that was a mistake in design. So two aircraft fell apart during the mid-flight in 1954. And the reason was metal fatigue. So the middle picture shows a section of the upper fuselage and showing the fatigue crack around the corner of a square window. And the crack propagated and eventually peeled the fuselage open and caused the aircraft disintegration. A finite element model shows a square window is a bad idea. You get a stress concentration in the red hotspots at the four corners of the window corner. So when we fly these days, we notice our windows on aircraft is round or even oval-shaped, not square-shaped. So this event has changed the face of commercial aircraft industry. Since 1950s, the Comet investigation has become the origin of many, many certification requirements that still applies today. So after 34 years of Comet accident, there was another accident with the operator Aloha, and that was a Boeing 737 aircraft. And that was 34 years after we designed against the fatigue. But this time, the aircraft actually landed with 1/3 of the fuselage peeled open and killing one flight attendant. The problem with this aircraft is the aging aircraft issue. Normally, the aircraft design life is 40,000 flights, but this aircraft actually flight about 100,000 flights and has accumulated many, many small cracks. So what you're seeing here on the right is a fuselage skin, so usually made by lap joints. But after aging, the adhesive become delaminated during the environment, also 100,000 flights. And all these fastener holes had developed very small fatigue cracks due to stress concentration. Each of these crack is very, very small, but when they are joined together, it's a big crack. And so the theory of Aloha accident from the FAA chief scientist, Professor Tom Swift lecture was the link up of multiple site damage. And that is an aging aircraft issue. So why holes gave us so much problems? So I just want to explain in the part 2 of my lecture, and that is stress racers. If there is no stress racer, there's no holes in the structure, whatever you applied remotely, the stress S, you will get internally the same stress. As soon as you introduce an open hole, like a window cutout, your stress increased by 3 times. And that is the classic solution. We call it a stress concentration factor, KT. And by finite element or by the photoelasticity experimentation, the value for open hole is 3. It's about 3. So if you apply a stress of 100 megapascal here, your local stress is 300 megapascal. But if we have cracks, for example, if the aircraft has a scratch mark or it has a dent, a sharp crack, the stress increase is even larger. And that will be solved by a fracture mechanics parameter called the stress intensity factor. That is not a stress concentration factor. So that requires some fracture mechanics equations, which I will return later. So for the moment, I will talk about holes. So the hotspot stress in the sigma max divided by applied stress is the stress concentration factor. So in my field, we call this notch effect. So it doesn't matter whether it's an open hole or pin-loaded hole, a riveted hole, or even a welded joint. We just call notch effect. So if you look at the dictionary, notch is an indentation, a dent. So the notch does have effect on structures because it has a stress concentration. So just talk about aircraft wing panel assembly. Traditionally, these were made by thousands of titanium fasteners. And this was the one tested at Cranfield University with a simulated crack. So next time you get on flight and just look out the window on the wing, you will see this pattern of riveted joints. And this was the example I took from the FAA lecture to Cranfield 10 years ago, and it actually shows a real crack developed from fastener holes. So the notch effect on Eisen curve is like this. Without any holes, your Eisen curve is this black curve, and that we tested by a smooth sample, and that is like a dog bone shape or hourglass shape. Stress concentration factor is 1. There's no stress concentration, and the material property developed. Eisen curve is called a material property. There's no geometric effect. As soon as you introduce a hole, you knock down the Eisen curve by a factor of kT. That's the stress concentration factor. So Eisen curve is much, much lower than the material curve. So if you apply a stress in this dashed line, on the material, you get a much longer life than you would get from the structure with the open hole. That is the orange line. So the stress rhesus actually reduce the material Eisen curve by a factor of roughly kT. So after I talked about holes, I just want to have one slide about a crack, because some of you will be dealing with crack growth, and that requires fracture mechanics. And there's another grandfather called Griffiths. He's a British scientist working in the Royal Aeronautical Establishment in the 1920s. And his theory is based on the strain energy release rate. And basically, Griffith's theory says, if the strain energy release rate G, that named after Griffiths, is greater than the energy available to create a specific surface, then the fracture will happen. So in terms of materials we have in engineering, there are 3 kinds of materials. There are brittle materials, very brittle. Then the free surface energy is 2 times of gamma S. That is the original Griffith theory. The most easy example for brittle material is glass. So if you have a scratch mark on the glass, you can actually break the glass. And in fact, no one wants to fly with a glass aircraft. It's very brittle. It cannot tolerate even a tiny small crack. So the middle ones is ductile metal. So that is our aluminum, titanium, steels. You get 2 beautiful plastic zones in the crack tip, and that absorb energy. So this butterfly shape is actually the plasticity energy dissipation zone. So that actually increased the fracture energy by a factor of gamma P. That means plasticity. So the fracture toughness increase enormously. So ductile metal can tolerate crack growth, can tolerate a crack. The last material is laminated composites. So you've got a 0-degree fiber, 90-degree fiber next layer, and the 45-degree in the further layers. In that case, it requires to define the fiber volume fraction and the matrix. And I will talk about this in my last lecture. The modern fracture mechanics most of us doing is developed by Professor George Irving in the 1950s. So we use stress intensity factor now in terms of K rather than G. And the fracture toughness is also in terms of K. But under linear elastic condition, there is a relationship between the Griffiths G and Irving's K, and they are related by Young's modulus E. So they are interchangeable in the analysis. So I think that concludes of my part 2 about notches that round the holes and also about cracks. So I just want to move to the technologies development, and that can enhance our capability to design against the fatigue. So I will talk about metallics first, and how can we reduce or even eliminate fasteners by advanced welding, by integral machining, or by large extrusions. And the latest one is additive manufacturing. That can reduce the part counts and the cost. And finally, I will move to carbon fiber reinforced composites. So just look at this Airbus picture. Before we have this A350 in our final lecture, a final part of my lecture, I just want to talk about this early aircraft. We're still flying them, and that is A320, got 15% composites, and A340, A330, it's not here. They got just around the 20% composites. So that means 80% of the current aircraft is still metal dominate. So the metallic materials on this aircraft are dominated by aluminum alloys. 2000 series are very good for fatigue resistance. So they are used for making wings and fuselage shells. 7000 series are used for spar, stringers, and ribs because they are high strength and high stiffness. We also have titanium alloys used for fittings and joints. Titanium alloy will increase as we introduce composites because aluminum has a galvanic corrosion problem with carbon fiber. So titanium usage will increase. And finally, steels are very heavy, and we are trying to avoid using steel. But this 300 M steel is used on landing gear, and that carries the aircraft weight at landing. And that is the highest strength steel currently we can have. So talking about advanced welding for joining materials, we have worked in about 20 years ago, in the millennium year, we had a project to replace these fasteners by a weld. So this is a lap joint. So you have to use more material to make lap joints. And these fasteners currently are titanium fasteners. They are heavy. So the project was use a butt weld here to join them. And that can save weight by about 0.8 kilograms per meter length structure. The second example on the right is the Airbus project I worked on also about 20 years ago, 15 years ago, and that to join two large extruded skin stringer panels. So each part has 3 stringers, and to join them by friction stir welding, which was invented by TWI in 1990. So that's 30 years ago, to make it possible to join aerospace grade aluminum alloys. So the next project I worked was a European project on the cost-effective integral structure. So the idea is to replace a fuselage skin and a stringer joint with fasteners. So on the left is the traditional joint, On the right was our research, and there are 6 concepts. So the first concept is have a friction stir welding rather than lap joints, but keep fasteners here. And the second concept is have a bonded fastener. Then the fourth one is have a laser welded fastener and friction stir welded skin. So anyway, we had a good fun, and to show all of these are feasible, also with much improved the structure weight. The next example I just want to show, at the same time Boeing was studying this integral structure. So the far left is a fastener assembled. You need about 10,000 of these fasteners on aircraft, but on the right is integral machine the structure. So the image is a bit like on the far right, without fasteners to reduce weight. The problem of this is the crack will initiate somehow in the surface, and it will grow because we have load variations in service. We should also have accidental damage like scratch marks or like impact damage. So integral structure has a problem. The lack of crack arrest capability because they don't have redundant members of structures. So damage introduced during service has to be tolerated. Therefore, we also need a damage tolerance design concept, and we also need a structure health monitoring. I've never worked on structure health monitoring, but I'm going to talk about damage tolerance next. So the project we worked on with Professor Mike Fitzpatrick at Open University and myself in Cranfield, and Dr. Kada Said was also on this project funded by the UK TSB Technology Strategy Board with Airbus, is to have some bonded crack retarders on the structure. So that retarders are redundant members. They will hopefully to retard the crack propagation. The retarder material was made of glass, and that is a glass, that was aluminum with glass fiber laminate. It's a hybrid composite. So the panel was made by Airbus, and this integral panel with 5 crack retarders in the middle bonded. And this was the 1 meganewton test machine in Cranfield University. And the fatigue life really shows this blue dotted line was without a strap. So this was the baseline of integral structure. And the pink dots were testing data of one of the strapped panel. And you can see the crack retardation is quite a lot. We also did the finite element modeling, fracture mechanics analysis, and with 2 different calculations of the stress intensity factor by either weight function or root mean square method, and we get some kind of good predictions. So finally, I just want to talk, the reason we calculate the crack length versus fatigue life is because we want to set inspection regime for the airline operators. So they will have a good time without inspection. So that is the crack before you need to do inspection. And after the first inspection, they schedule intermediate inspections like every 6 months. And that just makes sure any crack developed will be caught by inspections. So I think to conclude my metal fatigue lecture, I just want to mention laser shock peening for life improvement. This is not my work. This is the work by Professor Mike Fitzpatrick, Dr. Niall Smith, and the PhD Mitchell Leering at Coventry University. I have never done this, but I think this should be included in the modern technologies for design against fatigue. So what they did was using laser to introduce a beneficial residual stress, and that is in compression. So this was the X-ray synchrotron measurement of residual stress on the wing panel, on the aluminum panel. This gray surface is a zero stress line. So below that in blue is negative residual stress in compression, and that will cancel the applied tensile stress in service. So it's good residual stress, but good residual stress will be balanced by tensile residual stress because residual stress has to be self-balanced. So Mitchell, the PhD researcher, did some research. Currently, he just tried to have a different laser pinning pattern in different angles in relation to the crack here. The crack is horizontal. The laser pinning pattern is in different angles, different distance. And he calculated the stress intensity factor, that including the residual stress effect because it's K total. So that means applied plus residual stress. The fatigue crack growth rate on the vertical axis measured against the crack driving force K is like this. So without laser pinning, you get these orange colored dots. But after laser pinning, in this area with 4 different laser pinning patterns, you get a significant reduction of crack growth rate. And that means the crack fatigue life will be much longer. Remember, this is a log scale. So this gap is quite significant. It's about 1 or 2 magnitude reduction in crack growth rate. So my final 10 minutes, I still got 2 slides on additive manufacturing, then I will move on to composites. So additive manufacturing, most people are working on powder bed fusion. I had the opportunity to work with Cranfield University on the wire additive manufacturing. So that is an old welding technique to welding 1 millimeter diameter wire, layer by layer, to form an additive made part. And the advantage of this over the powder bed is they can make a large part, and the build time is faster than powder, and also 100% utilization of material. So there's no wasted powder unused after the fusion. So the example was the satellite propellant tank made by Cranfield, and now it's flying with the Airbus defense sector. So traditionally, if you want to make this tank by traditional forging, then machine off the interior and the machine to shape would take about, they say, take about a few months. But by additive layer, wire made, and afterwards polishing it is in terms of weeks rather than months. So what I had the opportunity in the last 2 years is the EPSSA funded a program grant called the New Wire Additive Manufacturing. And we work with the 3 other universities on the integrated program to answer the challenges in 7 research areas, from manufacturing challenge to material science and to process modeling. And at Coventry, we lead this area on the far right, lower right corner, and that is called the materials performance. The picture actually features if you have a defect, what will happen to the fatigue life of the parts. And we are in collaboration with Strathclyde University on non-destructive testing with ultrasound technology. So the PhD student Romali did this work. So the defect is a predominant failure source. Actually, we tested 2 types of defects. One is a process inherent, so that is we can't avoid. And this is the gas porosity with diameter smaller than 100 micrometers. But then the other type is anomaly defects. and that has a diameter of greater than 100. We introduce that by contaminated feedstock, and that is also a reality. So there's 2 micrographs shows the inherent defects and the anomaly one. Romali also did a stress analysis by finite element, and that shows by the porosity, the hot spot in red, the stress concentration factor is about 2. So the Eisen curve, the applied stress versus cycles to failure shows the blue group is either without porosity, that is a solid blue line, or with some inherent small porosity is the dashed line. That really means we can live with this. This is a process inherence and we can't avoid it. We can design to tolerate it. But the red and anomaly ones reduce the fatigue life by a factor of 2. So I think that concludes my metallic fatigue talk. I just want to have a quick summary. All the notches act as stress racers, and the metallic materials are highly sensitive to stress concentration effect. And material property is represented by the Volar curve. After 170 years, we still use the Volar curve. So advanced manufacturing in welding, large extrusion, adhesive bonding additive can all create a more efficient airframe, and that is called integral metallic structures. We have far fewer fasteners, maybe no stress concentration in the future, and the light weighting because no fasteners, and also low cost, no joint effort. The limitations currently, the integral structures has no crack arrest capability because they have no redundancy members. Additive manufacturing, people really worry about the defects. Also in homogeneous microstructure, I have not talked about this today. Some of these issues have been addressed by damage tolerance. Structure health monitoring is a big thing. I have not worked on this, so I have not talked about this. So my last 5 or 7 minutes, I will talk about composites aircraft, just in case you're interested. And that is the Boeing Dreamliner 787, and has 50% composites in this dark blue area. And Airbus responded with A350 extra wide body aircraft. And again, that is 52% carbon fiber epoxy composites. So the first thing I want to show you is the Eisen curve. This is all the data from British Aerospace. They actually tested carbon fiber, so they call CFC, so carbon fiber composites. And the Eisen curve really are flat. These top 2 lines are really flat. They really don't look like metals. You can see the metal Eisen curve, if you follow the mouse, is declining for steel and aluminum. The design limit load is here. That is the maximum design stress. So really, composite does not have a fatigue problem. They are above the fatigue limit. The reason of this is because epoxy resin has no plastic slip line. So they don't have dislocation, cyclic slip, like metal. And the carbon fiber epoxy laminate, they do not fail due to fatigue. The Eisen curve, again, from this book, is also flat. I just want to convince you. So the fatigue performance is much, much more superior to metals. However, there is a caveat. Only if composites in good condition, in pristine condition. Fatigue strength will drop significantly if we have impact damage, if there is a delamination, if the manufacturer has imperfection in the laminate, they call it manufacturing defects. So that has been my research for the last 30 years. from Imperial College to Cranfield to Coventry. So I've been working on impact damage, composite compression after impact, and the joint. So I have 4 slides. I will finish very quickly. I think this one is quite important. I just want to say composites has very poor interlaminar strength. That is about 10%, 5% of the implant strength. So horizontally, they are very strong. It's impossible to fail, but vertically easy to peel. Like you peel a banana skin, the strength is very low. So they're highly susceptible to impact damage. So I did about 400 tests in my postdoc time. And when you do the impact, you drop a hammer, you can see the delamination in the middle. The worst thing is barely visible. You can't see, the inspectors can't see. So after impact, tension doesn't matter, but compression is very critical because the delamination will open up. So we did a lot of testing. The real issue is the delamination is like cracks in metal. So that's the main message. So if you apply compression, delamination will open. And in the laboratory, we test them in the double cantilever beam to measure the fracture toughness value. And we also did a lot of modeling work by my PhD student on the stringers with cracks in the joint area. So the final slides just say the bonded joint is also not safe. The bonding line can have defects or even by impact. Impact has to be tolerated. That is a runway stone hit the aircraft or people drop hammers. So we actually use ultrasound to monitor these defects in fatigue loading until it become quite large after some 10,000, 100,000 cycles. So to conclude my lecture, I just want to say all the structure materials are highly sensitive to stress concentration. So for metals, these are the holes and the dents, pits, and the defects. Volar curve after 170 years is still the design curve for against fatigue. But if you have cracks, you use fracture mechanics. Composites is a delamination is always the issue. So we use fracture mechanics to design. A quick outlook for the future is both metal and the composites have their place in the current field aerostructures. And the metals we towards more integral structure, lightweight structure by modern technologies. And the composite is damage tolerance capability is the key, and the structure health monitoring is the big thing currently. And finally, I just say my group really want to embrace the green and the clean growth issue by being part of it, by doing a good job for damage tolerance analysis of any new materials. And finally, I want to thank all my PhD students, researchers at both universities, and my colleagues on the first 2 rows. I had a lot of technical interactions in my 6 years at Coventry University. And Professor Kappering and Nick provided good leadership and management to support my work. And in Cranfield, I just want to thank 3 professors who are really mentor to my early career, and Imperial College Professor Davis, and also all the sponsors. So thank you for listening, and I'm ready to answer any questions.
Thank you, Xiang, for a fascinating lecture, and congratulations on some excellent research there. I've just got one quick question for you before we go to the chat box. One of the things that I find really quite interesting is how we can design to resist fatigue. And shock peening, you talked about different structures of design. One of the things we heard a little bit about a few years ago was self-healing materials. Yes. Have any of those found their way into application? Because it seemed really interesting.
This was Professor Ian Bond in Bristol University. So he just buried some kind of capsules like your vitamin D in capsules, and they're like gel between the composite laminate. So if you do have impact damage, and this gel will release and kind of cool themselves in the room temperature. And Professor Ian Bond has 2 EPSRC awards about 15 years ago, another one 10 years ago on self-healing. So you can have a look of Ian's Bristol University Aerospace Engineering Department on self-healing. I'm not aware of other research in this, but Ian Bond is certainly a quite heavy figure on this.
Okay, thank you very much. So if anybody's got any questions they would like to ask Zhang, please can you submit those to the chat box? So we can see we've got a couple of questions there first. So I'll read the first one out. So it's from Kevin Vincent. So for the Comet, while square windows introduced stress razors, the actual crack failures were manufacturing defects in surrounding punched rather than drilled holes. So with the move to digital verification and validation, is there a way to simulate such fastening techniques with confidence in the results?
Well, that's a very good question. The Comet square window wasn't an engineering decision during the inquiry. It was operators' decision. They really like square windows to give passenger good experience. The defects and also the holes, and now we move to additive. I think I always feel my group is very destructive. We fail things, but we try to make you safe. But we also do a lot of simulations trying to understand. But currently, the safety factor for well-known materials is about 3. So we do cover any miscalculations or any failure mode nobody knows. But if there's a new material being introduced, no one has tested before, the safety factor is more than 3, is about 5. I don't know whether I answered your question or not, Kevin.
I'm sure that you can speak to Kevin afterwards if you did. Okay, thank you. So second question, in metal fatigue, 1, what is the physical significance of the dynamic response factor applied on fatigue unit loads? And 2, how is it effectively used in stress calculations?
Yeah, that's a good question. The first question is about the loading frequency. In aircraft, the frequency is very low. Next time you sit on aircraft after this pandemic, you can feel the wind. I always count cycles. It's about 2 cycles per second. It's half hertz. And the fuselage is 1 cycle per flight. So from here to China is 10 hours, just 1 cycle on the fuselage. But on the landing is more. And in the classic fatigue book, if the frequency in my test machine is below 50 hertz, frequency is not in the equation. Currently, the frequency is not in the equation for aerospace, but if you go to offshore, frequency is in the equation. If you do offshore fatigue, they use the frequency domain rather than cycle domain. So currently, we just count the cycles. So it's SNN standard for nine-mile cycle. We never had a time of frequency in any of our equations. So if my student want to accelerate, Kadar want to accelerate, it's 50 hertz in the fatigue testing machine, but we believe we can predict 1 hertz in aircraft because frequency is not a problem. So what's your second question? How is the effect?
How is it effectively used in stress calculations?
Stress calculation is quasi-static. So you get your stress calculation by static analysis, and your fatigue bit is S-N curve. But again, S-N curve is stress versus cycles. There's no frequency. If you're dealing with frequency, it's called vibration fatigue, like acoustic fatigue, the sound, like the tail plan on a military aircraft being the engine blew hot air. they have to take frequency into consideration. They don't call it fatigue, plan fatigue. They call it vibration fatigue. It's a different analysis method.
So I think we've got time for one final question before we finish. So Said Hidadime, Said, would you like to ask Xiang your question?
Yeah, hi, Carl. Hello, Zhang.
Hello.
I was wondering, you mentioned the application, the design approach for offshore structures which are taking into account frequency. But
yes,
we also know that frequency is not very much counted in the fatigue assessment of metallic structures in aerospace, for example, or in other areas. Is there any study, I was wondering, is there any reference we can look at why is that not significant to be looked at?
If you look at the Engineering Integrity Society, they call the Engineering Integrity Society in Sheffield. They are mainly working on automotive and offshore, and they work on frequency domain rather than the cycle domain. We work on cyclic, so frequency is not in our, and they work on vibration fatigue. So they work on the different spectrum. So they have plenty work. When I made a reference on frequency, I was referring on Professor Surish's book. It's called The Fatigue of Materials. And there is a section talking about below 50 hertz, and there is no effect on from frequency. So I know you very well, Saeed, so I can send you some frequency-related fatigue paper.
Yeah, that would be very good. Great, thank you very much, Xiang.
The good people are working in ENCODE. We have their ENCODE, so yeah, I can send you.
Okay, thank you.
Okay, good. Well, that brings us to the end of our hour. So thank you again, Xiang, for a wonderful lecture this evening, and thank you to everyone else for joining.